In this video, we're going to explore more about Lagrange multipliers. Let's look at this example. We're going to maximize f of x comma y equals 2x plus 3y, subject to the constraint that radical x plus radical y equals 5. And let's use the Lagrange multiplier method. So our f function, our objective function, we know that geometrically that just represents a plane. And then we have our constraint function, which we will rewrite as radical x plus radical y minus 5. And we need to find the gradient of each one. So the gradient of f is just the constant vector with components 2, 3. And the components of the g gradient are 1 over 2 radical x and 1 over 2 radical y. And remember that the gradient of f should be parallel to the gradient of g, and that gives us the following system of equations. So our general strategy is to solve for lambda in each equation. That should give us a relationship between x and y, which we can then use in the constraint equation to solve for x and y. So if I set lambda equal to each other, I'll get 4 radical x equals 6 radical y, which tells me that radical x is 3/2 radical y. And I'll just leave it in that form. I won't square both sides because in my constraint equation I have radical x. So replacing radical x with 3/2 radical y, get the following equation, and that one I can go ahead and solve for y. And I'll get y equals 4, and then go ahead and look at what is radical x. I'll get radical x equals 3, or x equals 9. So my solution here, my candidate solution, would be that the maximum value would be 30. But wait a minute here. I know that another feasible solution would be, instead of x equals 9 and y equals 4, I could also have x equals 4 and y equals 9, and that gives me a bigger value. So that can't be a maximum. I know I checked all my work, so what went wrong? Why did I not get a max value? And what is the max value? Well, let's go back to our graphical view of this method. Our constraint equation is a cylinder. Now remember, a cylinder for us doesn't mean a circular cylinder. It just means that we have essentially something like a folded piece of paper. And so that is the graph, the surface, representing our constraint equation. Now, one thing that is interesting about this graph is that the largest possible value for x or y is 25. And neither x nor y can be negative, and that's because of the radical signs. And now let's add the plane. That is our objective function. So let's add the plane in there. And what we're trying to do with this optimization problem is find the point, the point on this line of intersection between the cylinder and the plane, which maximizes, which has the largest z value, the largest 2x plus 3y value. And so just from this view, it looks like our candidate is clearly wrong, and that the largest value is going to be over here near the y-axis. All right, so let's take a look at another view. So here we're looking at, I've changed the scale on the z-axis to make it a little bit more tractable. The solid red is actually the plane, and the graph of intersection is this U-shaped, almost like parabola-shaped uh, curve right there. Now, according to this view, 9, comma 4, that z value actually corresponds to a local min, or an absolute min. For this case, it's an absolute min. And indeed, the maximum is over here on the above the y-axis. When y equals 25 and x equals 0, I get a largest z value of 75. And looking at this objective function, that seems to be what you would want to do, just intuitively. It's like, oh, I'm multiplying y by 3, I multiply x by 2, so I'd want to make y as large as possible. And that's what we did. So why didn't we find this solution, x equals 0 and y equals 25, using the Lagrange multiplier method? Well, let's go back to our problem here. Remember that what our gradient vectors were. And let's look at the gradient of g and what our maximum solution is. A solution occurs when x equals 0 and y equals 25. And now it should be a little bit more clear. The problem is the gradient of g is not defined when x equals 0 or when y equals 0. So the gradient of g is not defined. Even though x equals 0 and y equals 25 is in the domain of g, the gradient of g is not defined there. So that's why the Lagrange multiplier method is not going to find an optimal value if the gradient of f or the gradient of g is not defined at that optimal value. So that's a limitation of the Lagrange multiplier method. Let's look at an extension of the Lagrange multiplier method. What if I have two constraint equations? Let's start with an example. I'd like to find the point closest to the origin, which lies on both the cylinder, x minus 1 squared plus y minus 1 squared equals 1, and the paraboloid z equals 4 minus x squared minus y squared. So I have a cylinder. This happens to be a circular cylinder. It's centered at 1, comma 1, and a paraboloid. And I'd like to find a point which is on both of those surfaces that is closest to the origin. So for our objective function, closest really means shortest distance. But instead of using d equals radical x squared plus y squared plus z squared, that would be the distance from x, y, z to the origin, we're going to use d squared. It's just going to make all of the calculus simpler. D squared is going to equal x squared plus y squared plus z squared, and it will give us the same result in terms of x, y, and z, because maximizing d is the same as maximizing d squared, because the d squared function for positive values is increasing. So we're going to solve this minimization problem. We're going to minimize x squared plus y squared plus z squared subject to now both of these constraints. It must be on the cylinder and it must be on the paraboloid. So how can we go about solving this now that we have two constraints? Well, let's look at this again from a graphical point of view. So here I have gone ahead and graphed the paraboloid and the cylinder, and you can see their intersection. So we're looking for a point which is on the intersection of the cylinder and the paraboloid. And we want that point which is closest to the origin. So the intersection is this oval-shaped curve. It kind of looks like an ellipse. It might actually be an ellipse. Not really sure. Doesn't matter to the solution to this problem. So we're going to call our first constraint equation G and our second constraint function H. And at the point P on the curve, let's think about this. On our point P in the curve, that curve lies on both of those surfaces. So the tangent vector to the curve is going to lie in the tangent plane for the paraboloid and the tangent plane for the cylinder. So I didn't draw the planes here, but just imagine it, that the tangent vector to that curve, because the curve lies entirely on the cylinder, it lies entirely on the paraboloid as well. So at any fixed point, the tangent vector has to be, to that curve, has to be in the tangent plane for both surfaces. And that would mean, well, that the tangent vector is orthogonal to both gradients, the gradient of G and the gradient vector for H. So think about that, because remember the gradient vector can serve as a um, normal vector for the tangent plane at, to that particular surface. So that means that if t lies in the tangent plane, then it's got to be orthogonal to the gradient of g. But it's also in the tangent plane for the other surface, so it's orthogonal to the gradient vector of h. And we could say then that these two gradient vectors, if they're not parallel to each other, they're going to determine a plane, and that plane is normal to the curve. They, the plane containing gradient of g and gradient of h is the normal plane. And remember, given two non-parallel vectors, they are contained in exactly one plane. So the normal plane is the plane that is determined by gradient of g and gradient of h. All right, now that we've established that, let's just remove the surfaces and look at only the intersection, which is this curve. And let's look at the objective function. Well, the graph of the objective function, if I look at the objective function, really, it has three input variables and one output variables. So its graph lives in 4D. So we can't sketch it, but we can sketch the level. I say level curves. I really wanted to say the level surfaces here. Let me go ahead. I'll have to make some corrections. So let me go ahead and rewrite this. So our level surfaces look like x squared plus y squared plus z squared equals k, and that is the equation of a sphere. So here's one level surface right here, and I believe it corresponds to when k equals 3. So the radius of the sphere is radical 3. So these three, even with technology, it's hard to see that at this point there's actually space between the sphere, the level surface, and the curve of intersection. And so now just one more correction here. So if I find a level surface that is tangent, so barely touches the curve of intersection of my constraint surfaces, then what can I say? Well, the tangent vector to the curve is now the surface just barely touches its tangent to it, meaning that the tangent plane contains the tangent plane to the sphere now is going to contain the tangent vector to the curve. So that means that the gradient vector is going to be the gradient vector for the sphere now. So gradient of f is going to be perpendicular to the tangent vector. And that means that it must lie in the um, normal plane. So again, let me say that again. We've got a level surface that just touches the curve, and that would mean, what does it mean? It's tangent, so the tangent plane to the level surface contains the tangent vector to the curve, and since the gradient vector can serve as a normal vector to this tangent plane, then that normal vector has to be perpendicular or orthogonal to every vector in the plane, so it's orthogonal to the t vector. But all of the vectors orthogonal to t are in the normal plane for the curve at that point. And since that normal plane to the curve is the plane determined by the gradient of g and the gradient of h, then we can write the gradient of f as a scalar multiple of the gradient of g plus a scalar multiple of the gradient of h. And let me remove this. So the two multiples we're using, we're going to use lambda, the Greek letter lambda again, as our multiplier on the gradient of g. We have a second multiplier then, and that is the Greek letter mu. So now I have two Lagrange multipliers. And so when we have two constraints in our Lagrange multiplier method, our technique for solving this is to solve the system of equations. Well, I need to have the gradient of f equals a multiplier times the gradient of g plus a different multiplier times the gradient of h, and then we have our two constraint equations. So in this case, you're going to have a system of 5 equations. So I'll get 3 equations from the gradient condition, and then plus my 2 constraint equations. That's a total of 5 equations and 5 unknowns, x, y, and z, mu, and lambda. And as before, the method will fail if the optimal value uh, is at one of the points where the gradient of f, the gradient of g, and or the gradient of h does not exist. All right, So now let's use this technique that we just learned about in our example problem. We're going to try to minimize x squared plus y squared plus z squared, subject to the fact that that point has to be on both the cylinder and the paraboloid. So we'll need to find three gradient vectors: gradient of f, gradient of g, and the gradient of h. And we'll use the fact that the gradient of f is a multiplier times the gradient of g plus a different multiplier times the gradient of h. And now we'll get this following system of equations. So let's see how we could reduce that first. I can see a common factor of 2 on both of these equations. So let's reduce those to the following equations. And on those reduced equations, now I've got two Lagrange multipliers. So again, I'm going to follow the same type of uh, scenario or type of strategy that we used before. I'm going to solve for my Lagrange multipliers. That should give me a relationship between x, y, and possibly z, but there's no z here just because of the nature of one of the constraints. And then I can use that relationship in my constraint equations to solve for x or y. So I'm going to use the elimination method since I have two variables here that I want to try to solve for. So I'm going to eliminate mu and solve for lambda. So to eliminate mu, I can multiply the top equation by negative y, multiply the bottom equation by x, and so that gives me mu times x, negative mu times xy in the top, and positive mu times xy in the bottom. So when I add those together, there's no more mu. I went ahead and multiplied out or removed the parentheses here in the two terms that do have lambda in them, and rearranging that, I get 0 equals lambda times the quantity y minus x. So here we'd have either lambda equals 0 or y equals x. Now, one thing that's different about this method from when I have only one constraint equation, if I have only one constraint equation, lambda has to be a positive number or non-zero number. It can be negative. Lambda cannot equal 0. But with this method, it's fine for lambda to equal 0, and we'll talk more about that later. Or y would equal x. So if I take y equal to x, and I put it back into the equation for the cylinder, then the two terms become identical. I can add them together. I'll get 2 quantity x minus 1 squared equals 1. And I can solve that for x. So x will equal 1 plus or minus radical 1/2. And radical 1/2 is going to be radical 2 over 2. And that must equal y as well, because that's how we got that value. And now to get z, I'll use my other constraint equation. So when x in y equals 1 plus radical 2 over 2, then put that into the equation for the paraboloid, and I will get 1 minus 2 radical 2. And then I can take the other value I had for x and y, which is 1 minus radical 2 over 2, and put it back into the equation to get 1 plus 2 radical 2 for my z value. But I've only eliminated mu here. What happens if I eliminate lambda? Well, if I start out here and I multiply the top by negative quantity y minus 1, multiply the bottom by just parentheses x minus 1, then I see that in the top equation, I have negative lambda, parentheses x minus 1, parentheses y minus 1, and I'll have positive lambda, parentheses x minus 1, parentheses y minus 1 in the bottom equation. And so when I add them, I'll get a new equation which does not have any lambda in it. And as I did previously, I went ahead and removed the parentheses in the remaining terms. And I can rearrange those as follows, which tells me that 1 minus mu times quantity x minus y equals 0, giving me the solution that either mu equals 1 or x equals y. Well, we already explored x equals y, so let's find out what happens when mu equals 1. Now, I recognize that there's many ways that you can go about solving the system of equations. And so there might have been a shorter way to reach this mu equals 1. And if you found that shorter way, then that's great. But we've arrived at mu equals 1. So let's go ahead and see what solutions that will bring. So in mu equals 1, if I go to this third equation from the gradient condition, it gives me that z must equal 1/2. So when z equals 1/2, um, just thinking geometrically to our line of intersection there should be 2 points. So let's see if we can find them doing some algebra. So I'll put that into the equation for the paraboloid. That doesn't give me a direct solution for x and y, but it does give me a relationship for x squared plus y squared. That's going to equal 7/2. Well, how does that help me? Well, if I expand my equation for the cylinder and collect like terms, I can put the x squared plus y squared together, then I'll have the linear term, and then that I'm going to set that equal to -1, right? I had a 1 plus 1, which would be 2. 1 minus 2 will give me -1 on the right-hand side. Now I can replace the x squared plus y squared with 7/2. This still does not get me a value for x or y, but I can solve and get a relationship between x and y, which is now linear. So I'll have x plus y equals 9/4. And I can solve that for y. Y will equal 9/4 minus x. And I'm going to go ahead and put that back into our relationship here. The x squared plus y squared equals 7/2. And multiply that out using FOIL, collect the like terms, make one side 0, so I can use the quadratic formula. And that simplifies to x being 9 plus or minus radical 31 all over 8. And we're not asked to find a decimal approximation, but it is useful to see, you know, uh, you know, what are these x values? Do they look reasonable? And they certainly do. All right, so I've got my exact x values, 9 plus or minus radical 31 over 8. And I know that y equals 9/4 minus x. So let's just work through the arithmetic then to calculate what the corresponding y values are. So I'll write with a common uh, denominator here. It should have said 8. So I'm going to have some updates to make here. 9 over 4 is clearly 18 over 8. And so 18 over 8. Now I've got that common denominator. 18 minus 9 will give me 9. When I multiply plus or minus radical 31 by -1 here, or distribute the minus sign, I'm still going to get plus or minus, but in the opposite order. So we write that as minus plus radical 31 over 8. So that can be a little confusing. So really what that says is that when x is 9 plus radical 31 over 8, y is going to be its conjugate, 9 minus radical 31 over 8. And likewise, when x equals 9 minus radical 31 over 8, y will be 9 plus radical 31 over 8. All right, so let's write down, we have actually found 4 ordered triples, 4 values of x, y, and z, and we have to determine which one corresponds to the closest point. So we'll go ahead and put it back into our objective function. And we can simplify this objective function um, using one of our constraint equations. It's not really part of the solution. It's just to make the uh, evaluation of the objective function a little bit simpler, because we have those uh, somewhat complicated expressions for x and y, and frankly z as well, but now we're only dealing with one of those expressions. So I would rather not square out 1 plus radical 2 over 2 and then also have to square out 1 minus 2 radical 2. So I only have to do that once here. And that gives me the solution 12 plus 2 radical 2. Our second solution, and this occurred from when x equals y, right? We got 2 solutions. And so now I have the conjugates for both x, y, for all 3 x, y, and z. And I'll get 12 minus 2 radical 2 for my objective function. So from when mu equals 1, remember I got z equals a half. So using this form for the objective function is really going to help us out here. And so that evaluates to 15 over 4. And if I use the conjugates for x and y, still at the same z value, I get the same value from the objective function. And so I get 3 different values here. And geometrically, that's telling me that there are 3 level surfaces tangent to the curve of intersection. So I have a level surface that actually uh, is tangent to the curve of intersection at 2 points, these 2 points right here. And then there's another level surface with a greater radius where it's tangent to the curve at this point. And then finally, there is a third level surface which is tangent to the curve at that point. And so again, we have solved the problem. We found actually the 2 points that are closest to the origin. So why would I go through this? Clearly, there are several other ways I could have solved this problem. Well, if I have many constraint equations with many variables, then the Lagrange multiplier method is one of the ways that you can easily solve using technology. So even though solving this problem by hand probably would have been easier to choose a different method, it is something that you can automate for larger and more complicated problems.